Hello again. So for part 3 of section 1.4, we are going to begin with what is called the squeeze theorem. Okay, and this is actually example 9 in your book, but I think this is an important concept, so we're going to walk our way through it. It's good for you to see, it's good for you to understand the logic that's behind it, because you will be required in future courses to apply logic like this. But for the purposes of our class, you are not responsible for the squeeze theorem, but you are responsible for the results that come out of the squeeze theorem. I'll point those out to you, what it is you're responsible for, but you can use the squeeze theorem if you want to, but you're not required to do so. So the question they have is, I would like to find out what the limit as x approaches 0 is of x squared sine 1 over x. All right. Now, if we try to put 0 in, we could put a 0 in here where x squared is, but this 1 over x, if I put 0 in there, it's actually out of the domain, correct? And the sign of anything, it just oscillates along and keeps repeating itself every 2 pi. So this is sort of a problem where you're not real sure what you're supposed to do with it. So they use the concept of the squeeze theorem. And so let me tell you what that is. So let's say that I have some equations, and I know that f of x is always going to be below some value g of x, which in turn is below, let's say, h of x throughout, or at least in a particular area that I'm interested in. So in effect, what you have is f of x could be doing something like this. G of x is maybe doing something like this for that moment. And let me do this again. Okay, so f of x is down below because it's less. Sorry about that. I was trying to change colors, and I need to look at where I'm drawing my lines. And then h of x is above, so it looks like that. Okay, so here's h of x. Here is f of x. And here's g of x. And let's assume that I can understand what h of x is doing, and I understand what f of x is doing. I don't know what g of x is doing, but I know that just for this one little moment in time along its whole existence, it's squeezed in between these two. Okay? Now, if that's true, and if I can prove that's true, then whatever these two are doing, okay, so whatever value this is approaching right in here, and this one's approaching this value right in here, if this one's squeezed in between, it has to be approaching that same value. And that seems kind of like, okay, well, that's logical, but how is that exactly going to help us? All right, so here's how it helps. Okay, do we know for sure, is it for sure, that whatever's going on with sine of x, that it's going to always be between 1 and negative 1? Is that true? Does sine x always bounce around between negative 1 and 1? Yeah, that's true. Okay, so technically, sine of x is bouncing along like this, between negative 1 and 1, right? So sine is squeezed in between these two values, right? Now, if that's true, then basically this doesn't have to be just sine of x, because you could have thought of it as sine theta, right? Where sine theta, or sine of x, could also be this 1 over x. It's kind of a little unexpected, because sine of anything, whether it's x or theta or 1 over x, whatever it is, it's going to bounce around between negative 1 and 1. Okay, so we're okay so far? So we know that this is true, but what I'm trying to figure out is what's going on with sine of x multiplied by an x squared, right? So what we first have to do is accept that this is true, that there is a squeeze theorem going on, okay? Then we try to manipulate it to where it looks like this right here. So what I would have to do is multiply all the sides by x squared. So x squared times this x squared times this, and x squared times this. And sometimes I just do not understand why it comes up with these ovals and circles and stuff. I swear, we will all get used to each other. I'm going to try something real quick. Okay, all right, I learned something new. Okay. And here's my x squared there. So if I multiply these out, now remember, if we multiply by a negative number, we have to reverse the inequalities, but x squared is always going to be positive because when you square a number, it always turns out to be positive. So a negative 1 times a positive x squared is negative x squared, less than or equal to x squared sine of 1 over x less than or equal to x squared. Would you agree that's what we've got? Okay. Now what original question was, what is the limit of this part right here? True? So maybe I can tell what the limit of minus x squared is as x approaches 0. Do we know what that is? Well, minus x squared is actually a parabola that turns down like this, right? And so what's the limit of minus x squared as x goes to 0? It's 0, isn't it? Okay. So what's the limit as x goes to 0 of x squared? So x squared is a parabola that looks like this. Agreed? So what is the y value approaching as x gets close to 0? It's 0. So if the limit of this is 0 and the limit of this is 0, then what do you think the limit of this has to be? According to the squeeze theorem, then this has to be squeezed in between, and this is the answer. You okay so far? So we started off with what our question was. We used the squeeze theorem. We started off with something we know for sure to be true. We then manipulated it algebraically to come up to the form that we wanted, and we had our answer. Now you are not responsible for this, and you do not have to use the squeeze theorem for me. But if you look on page 42, okay, they go through a geometric proof of the squeeze theorem, and they come up with this concept: the limit as theta goes to 0 of sine theta over theta is equal to 1. And they show you how that goes. And it's a really kind of a complex proof unless you're really into geometry. You're welcome to read through it. We are not going to cover it in this class, but you are responsible for this. So you're responsible for knowing this. You have to memorize this. And we're going to use this in section 1.4, and it will be on your test, and you'll see it in the future, so you have to keep up with this. They've also sort of hidden on page 43. So on page 43, in example 11, they hide the limit as theta goes to 0 of cosine theta minus 1 over theta equals 0. Okay? And you have to know this. So even though you don't have to know the squeeze theorem, you have to know these two things which come about as a result of the squeeze theorem. All right? Now let me point out to you what this is kind of saying. So what this is saying is if you take sine of something, whatever that something is, and you have that same argument down here. So if this was 3x, this has to be 3x. If this is 2 theta, this has to be 2 theta. So if these two things match, and if you're coming up to 0, and only when you're approaching 0, you get 1. So if you have this, and surprisingly, this happens fairly often. So theta has to be approaching 0, not something else, okay? And these two, the argument has to be here, and here has to be an exact match. And here, theta is approaching 0 and only 0, and you have to have this has to match this. So for the cosine minus 1, you get 0, and for sine, you get 1. Okay? All right. So what are we going to use this for? Let's look at problem number 49. And problem 49 says the limit as x approaches 0 of sine 3x over x. And we want to know what that is. And you remember how in early parts of 1.4 we would factor, we would multiply, we did all sorts of things to try to maneuver it into a simpler version. Well, what I'm trying to manipulate this is I look at it and go, you know, this looks an awful lot like this sine theta over theta, except they don't match. This one is a 3x, and this one down here is an x. And if they matched, the answer is 1. Okay, so is there some way to make this down here be a 3x? And then they match. Well, I could have a 3x down there and multiply by 3 as long as I multiply the numerator by 3, so that I'm multiplying by a version of 1, right? So this is the limit as x goes to 0 of 3 sine 3x over 3x. Would you agree? And these two match. Okay, and if those two match, then this part right here goes to 1. And what you have is 3 times 1. So the answer is 3. You okay? And I'm perfectly happy if you just draw a line like this through here and say, and this arrow says goes to 1, and that's a normal accepted way to name things. At least for most people it is. If your teacher has some sort of a fit about it in future classes, just don't do it. But most teachers will do this. Okay, so the limit as sine 3x, and it's very prominent in physics and engineering. Okay, so what's the answer to the question of what's the limit of sine 3x over x? It's 3. So always go back to the initial question, not the one that you changed it into, but go back to the initial question and say, and the answer is 3. Is everybody okay? Let's do another one. So let's do 54. And 54 says the limit as x goes to 0 of sine 3x sine 5x over x squared. And when you see this combination of x going to 0 and then you see sine of something, your instinct should be to try to maneuver it or manipulate it into this concept of sine of something over something. Okay, so this one is a 3x and needs a 3x underneath, and this one is a 5x and needs a 5x underneath. Would you agree? Okay, so I can do that in this way. So here's the limit. Remember, you can go over 1 equals worth on your homework. And you would have sine of 3x, sine of 5x, and an x times an x here. And so I just split the x's up so at least everybody has an x, right? Now this one needs a 3, and I would multiply the top by 3 to be multiplied by a version of 1. And this one needs a 5, and I would multiply the top by that to be multiplied by a version of 1. So this is now the proper form. Sine of 3x over 3x as x goes to 0 is 1. Sine of 5x over 5x is 1. So this turns out to be 3 times 1 times 5 times 1, so the answer is 15. So the limit as x goes to 0 of sine 3x sine 5x over x squared is this. And you're welcome to do circles if you like that better. All right, try to make the circle go outside the 15 instead of, I don't understand the software. Now, it's the same thing if you had the limit as x goes to 0 of, let's say, x over sine of 2x, right? So flipping it upside down like this, you would still need this match of having these two x's. So you would multiply the bottom by that as well. So you'd be multiplying by a version of 1. And then this matches, okay, and goes to 1 because 1 over 1 is still 1, right? And so you would have 1/2 times 1, it would be 1/2. So it can be flipped upside down or kind of right side up if you think sine needs to go on the top, and that would be just as well. Everybody's okay so far? Okay. So let's look at 53. And 53 says the limit as x goes to 0 of sine of 3x over 5x cubed minus 4x, right? And so we've got that 0 and we've got the sine of 3x. Maybe we could factor out an x. And we'd have sine of 3x over x times 5x squared minus 4. And what I would need is a 3 down here. So multiply this by 3 to get a match and multiply the top by 3 so it's a version of 1. And then this is going to go to 1, correct? So you would have 3 times 1 over 5 times 0 squared minus 4. So this would turn out to be negative 3/4. Okay, all right. And then just to sort of give you a heads up, here's 51. So if you have the limit as t goes to 0 of tangent of 6t over sine of 2t. Okay, now what's sine of 2t if t is 0? Well, sine of 0 is 0, so we've got 0 in the denominator. I've not done one of these with a tangent in the top. You cannot take sine of 2t and cancel it into a 6t anything, right? So if we break this down into sine and cosines like you do for proofs, this sine of 2t does not cancel into sine of 6t. It may look like we do this at the end, but that's really not what's going on. Okay. So you would have the limit as t goes to 0. And to divide by sine of 2t is the same thing as multiplying by the reciprocal. So we could, or you could just drop the other denominator down. Some people think of it that way. So you would have cosine of 6t comes down here with the sine of 2t. Everybody's okay so far? All right. Now, so these don't cancel, right? So I don't have any t's, to make them up with. Sine of 6t would want a 6t down here. Sine of 2t would want a sine of 2t down here. And let's talk for just a second about this cosine of 6t. Is that a problem? Can I leave that down there? What if t is 0, you'd have cosine of 0. And what is cosine of 0? Well, it's 1. So this is actually okay. It's these other ones that cause me problems. So what I would do is have the limit as t goes to 0. And I would split these up. So I would have sine of 6t over 1. And I need a 6t down here in the bottom so that they have their match, right? So I'd have to multiply by 6t on the top to have a version of 1. Okay? Then I'd have 1 over cosine 6t, which is okay, because as t goes to 0, this is going to be 1 over 1. And then I would have 1 over sine of 2t, and it needs a 2t to match up with it. So I would have to multiply by a 2t down there to be multiplied by a version of 1, correct? So these are a match, and these are a match. So what I've got is this is going to go to 1 times 6, right? Everybody with me so far? T times 1 over cosine 6t times 1 over 2t. Let's leave the limit in there for a minute. I was going to go ahead and reduce it a little bit more quickly, but I think there's a lot going on here, so let's do it a little bit slower. So this is going to go to 1. This goes to 1, but I still have these 6t's. This 6t is this one. This 2t is this one. Okay, everybody with me so far? So the 2t that's on the bottom, I can't leave 0 in the bottom, right? That gets me back to the same problem. And if I can't make it go away, I have to sneak up on it. And so what I'm going to do, though, is I can say this t cancels this t. Everybody with me so far? So now I'm all good. I'd have 1 times 6 times 1 over 1, right? Times 1/2. So 1 times 6 is 6, times 1 is 6, times 1/2 is 3. So this turns out to be 3, which makes me look like I could just reduce that up there, okay? But it doesn't always work that way. Everybody's okay? This was kind of a complex, kind of vague kind of problem. There was a lot going on in here about manipulation. So be sure and kind of take your time with this problem, and be sure and do some exercises out of your book, because you'll have to do 1 or 2 of these. Okay? All right. So that concludes the lecture over section 1.4.